Hello, physics students. We're looking at Chapter 10, Interactions and Potential Energy. So the goal of this chapter is to develop a better understanding of energy and its conservation. Preview: how do interactions affect energy? So again, we talk about this. We talk about defining a system versus the environment that's outside the system. We continue our investigation of energy by allowing interactions to be part of the system rather than external forces. So if you have two objects interacting, you could define the system to be one of those objects, or you could, and then the other object would be part of the environment, or you could define the system to include both objects, and then the interaction will be part of the system. You will learn that interactions can store energy within the system. Further, this interaction energy can be transformed via the interaction forces into kinetic energy. What is potential energy? Interaction energy is usually called potential energy. There are many kinds of potential energy, each associated with position. There's gravitational potential energy that changes with our height above whatever the gravity is coming from. Usually we're talking about the Earth. So as you get higher above the Earth or farther from the center of the Earth is another way to put that, you have more and more gravitational potential energy. Another is elastic potential energy that changes with stretching, something like a spring that changes with stretching or compressing the spring. All right. When is energy conserved? If a system is isolated, its total energy is conserved. All right, let's say that again. That's a really important thing. If a system is isolated, its total energy is conserved. That means if it's not isolated, then perhaps its total energy is not conserved. What does it mean for a system to be isolated? A system is isolated when it is not interacting or acted upon by anything outside the system, by anything in the environment. If a system both is isolated and has no dissipative forces, its mechanical energy, K plus U, kinetic plus potential, is conserved. So in this case, K initial plus U initial equals K final plus U final. In this interaction, all of the kinetic energy on the left side of the equation is now converted into all potential energy on the right side of the equation, and it's the exact same balance that it was before, as far as the total. All right, notice this says when there are no dissipative forces. Dissipative forces like friction cause a different kind of energy to happen called thermal energy. And so in subsequent chapters, this accounting relationship right here will also include a thermal energy indicator as well as kinetic and potential. What is an energy diagram? So I guess we would call this an energy chart or an energy bar chart, whereas this would be an energy diagram. It's a graphical representation of how the energy of a particle changes as it moves. So not over time, but over some displacement or distance or movement. Notice the x-axis is not time, it is actually x, which is some kind of a measurement of distance. Turning points occur where the total energy line crosses the potential energy curve. And potential energy minima are points of stable equilibrium. All right, that's a confusing concept. It can become more clear to us as we go. Turning points occur where the total energy line crosses the potential energy curve. All right, just a little bit of a hint about how to think about this. The total energy of a system remains constant. Of an isolated system remains constant. Now, if there's that's what's represented in this constant line right here. If there is an interaction from outside the system, if something in the environment does something to the system, then that total energy line could go up or down. It could move. It could translate up or translate down based on that. But in an isolated system, which is what we're probably thinking about here, that total energy remains constant. This curve represents only the potential energy. So as this potential energy changes, there has to be an accounting for that to maintain the constant total energy. So as potential energy here goes down, one of the other kinds of energies has to be going up, like kinetic, or maybe even thermal, or maybe even both. And as the potential energy rises here, that means that the other two energies will in some way have to fall. And this is a little confusing. The potential energy here goes above the total energy, which means there has to be a negative kinetic or a negative thermal energy happening to account for that. If that was going to be the case, that's kind of a strange situation. All right. So the part about turning points, like a turning point in an object's movement. Think about a ball going up and then getting to its apex and then turning around and coming down. When it reaches its apex, that is a maximum. That is when potential energy the total energy of that ball is all potential. So the potential energy would intersect the total energy line right there because they would be equal. And then as the ball comes back down, the potential energy decreases then and kinetic energy increases. You could also think about it as a spring. Same thing for a spring. As the spring stretches to its maximum stretchiness, that potential energy has then reached its maximum. And the whole energy of the system is all potential. The object is not even moving for a short, for an infinitesimally small moment. Then the spring begins to draw back, and the potential energy will decrease. The kinetic energy will increase because the object is going to be moving and going faster and faster as the spring draws itself back to its equilibrium position. How is force related to potential energy? Only certain types of forces, called conservative forces, are associated with the potential energy. And for these kinds of forces, conservative forces, the work done changes the potential energy according to this formula. The work, or the negative of the work, is equal to the change in potential. Now, in the previous chapter, we looked at the external work being equal to the change in kinetic. Well, this time we're looking at a work actually causing a change in potential. Force is the negative of the slope of the potential energy curve. So here's the potential energy curve. The force is the negative of the slope of the potential energy curve. So whatever the slope of this tangent line is, that's that slope. The force is the negative of that slope. We'll try to understand that better as we go as well. Where are we now in our study of energy? Energy is a big topic, not one that can be presented in a single chapter. Chapters 9 and 10 are primarily about mechanical energy and the mechanical transfer of energy via work. So mechanical energy being kinetic and potential. And mechanical transfer of energy via work. We've touched on thermal energy because it's unavoidable in realistic mechanical systems with friction. These are related by the energy principle, and here it is. Change in energy of the system is equal to the change in kinetic plus the change in potential plus the change in thermal. And all of that change is going to occur due to and equivalent to the amount of work done on that system by external forces. Part 5 of this book, Thermodynamics, which we won't get to, but ponder it, will expand our energy ideas to include heat and a deeper understanding of thermal energy. Then we'll add another form of energy, electrical energy, in part 6, which again, that's saved for further physics classes. All right, reading questions. A particular interaction force does work internal inside a system. The potential energy of this interaction is U. Which equation relates U and the internal work? All right, if we think about work as being force times distance, think about a ball going up into the air. Which way does the force point? The force points the opposite direction of motion. It points down. So that's a negative force, which would make that become a negative internal. If you consider the earth and the ball as a single system, all in the system together, then that's an internal work done, and it's a negative work done. And that's going to equal the change in potential energy as the ball goes up. It's increasing in potential energy. All right, gravitational potential energy is what? Alright, the area under a force versus time graph, that would not be the case. Force, that would be like force times time. Energy and work don't have to do with time, they have to do with distance. So maybe a force and distance, we might have something. The gravitation constant times the mass squared divided by the distance squared. No. That would be more just about gravitational force. C, mass times the acceleration due to gravity, so mg, times vertical position, so times the distance. So we're talking about force times distance there. That's looking like a good answer. 1/2 mass times speed squared. That is kinetic energy. We know that to be the formula for kinetic energy. Velocity per unit mass doesn't sound right. I think it's C. It is. So that is exactly what gravitational potential energy is. It's basically the weight in newtons times, or the force of gravity, the same thing as a weight. The force of gravity times the distance above the Earth, which is the vertical position. 10.3. A method for keeping track of transformations between kinetic energy and gravitational potential energy introduced in this chapter is what? We already looked at this in the preview. Energy bar charts. Keeping track of the transformations between kinetic and potential energy bar charts. 10.4. Mechanical energy is what? It is D, the sum of kinetic plus potential energy. That's what we classify as mechanical energy. So thermal energy would not be a part of what we call mechanical energy. It's just basically the two categories of kinetic and potential. 10.5. For conservative forces, force can be found as being the negative of the derivative of potential energy. Remember we looked at that earlier? The slope of potential energy, the negative of that slope is equal to the force. So, alright. Potential energy, action-reaction pair of forces. So there's some kind of action-reaction forces going on with A and B, like a ball hitting a bat, or you pushing on the earth with your foot in order to walk. Alright. External forces do work on the system. So you could define the system this way. You could define the system as A has its own system and B has its own system. And if that's the case, then the force of B on A is an external work done on object A, and the force of A on B is an external work done on object B. The other way to define the system is to define A and B together into a single system. Then this is not an external work, it's an internal work. It's an internal force, not an external force. Both of those forces, A on B and B on A. Consider two particles A and B that interact with each other and nothing else. There are two ways to define the system. System 1 consists only of the two particles. The forces are external, and the work done by the two forces change the system's kinetic energy. System 2 includes the interaction within the system. Since the external work would be 0, we must define an energy associated with this interaction, and we call that potential energy, U. When internal forces in the system do work, this changes the potential energy. Consider two particles A and B that interact with each other and nothing else. If we define the system to include the interaction between the particles, then as these forces do work, the potential energy changes according to this. Change of potential energy equals the negative internal work, which is the negative sum of the work of A and the work of B, where it's the total energy. The system's kinetic energy can be increased if its potential energy decreases by the same amount. In effect, the interaction stores energy inside the system with the potential to be converted to kinetic energy, hence the name potential energy. Gravitational potential energy. The figure shows a ball of mass m moving upward from an initial position yi to a final vertical position yf. Let's define the system to be the ball plus the Earth, including their gravitational interaction. This introduces an energy of interaction, the gravitational potential energy, U sub g, which changes according to this, which we just said. Where W sub b is the work gravity does on the ball, and W sub E is the work gravity does on the Earth. Okay. So in this example here, the ball starts at here, starts at yi. The force is pointing down, but the ball is actually moving up. The ball starts at y sub I and ends at y sub f. And so delta y is this blue vector here. The work done on the Earth is practically zero, since the Earth has almost no displacement as the ball moves. We all get that. The force of gravity on the ball is negative mg. So as the ball moves up a distance delta y, the gravitational potential energy changes according to this equation. The change in potential energy due to gravity, gravitational potential, is equal to negative of the work done by gravity on the ball. And the work done by gravity on the ball is the force of gravity times the distance that it goes. Mg is the force of gravity on that ball. Delta y is the movement that that ball undergoes while undergoing that force. Define gravitational potential energy as an energy of position. And here it is, mgy, or mg delta h, sometimes as it's referred to. Delta h being the change in height that the object undergoes. The sum, kinetic plus gravitational potential, is not changed when an object is in free fall. Its initial and final values are equal. The final sum of kinetic and potential is equal to the initial sum of kinetic and potential. So example 10, launching a pebble. Raphael uses a slingshot to shoot a 25-gram pebble straight up at 17 meters per second. How high does the pebble go? We can use this energy balance to figure this out. What is the so at the beginning it's all kinetic. We got to end at the beginning. All kinetic. That's when he first shoots the pebble and it's going at its fastest. But at the end, I'm defining the end here to be, according to the question, how high does it go? The end would be when it reaches that highest point. When it reaches that highest point, the ball is not moving at all, sorry, the pebble. In which case, it would be all potential. Now, you don't have to write that down. I'm just writing it down to give you the concept here. But basically, it's this. Ki plus Ui equals Kf plus Uf. Another way to write that is delta K equals delta U. You could write it like that too. That would be Kf minus Ki equals Uf minus Ui. Actually, this would be, one of these would need to be negative. We could make that one negative or the other one. All right, so what is the kinetic energy of the ball at the very beginning? It is 1/2 mv squared, right? K is 1/2 mv squared. So it's 1/2. 25 grams would be 0.025. And V would be 17 squared. What's the initial potential energy at the very beginning? We could define the very beginning potential energy to be when it's to be 0. We could say that its initial position, initial height being 0. Okay, so that equals, what's the final kinetic energy? When it's at its highest, the ball's not moving at all, V would be 0. So the final kinetic energy is 0, which is what I said earlier, all kinetic at the beginning, all potential at the end. What is the final potential energy of the ball? It's mg delta h, or mgh, or whatever you want to say. Which would be, or we could say mgyf. So m being 0.025 G being 9.8, and YF is what we're looking for. So we only have one unknown and we can solve for it. Just do the algebra there. And if you do that algebra, just 1/2 times 0.025 times 17 squared divided by 0.025 divided by 9.8. Would give us 15 meters. Okay. Notice here's another way to do the accounting. The change in kinetic plus the change in potential has to equal 0. That's another way to say it. Which is what I said kind of earlier with that. The change in potential, the change in kinetic equals the negative change in potential. The change in kinetic equals the negative change in potential. All right. Quick check 10.1. Rank in order from largest to smallest the gravitational potential energies of the balls. Okay. Remember, potential energy is energy due to the position. Gravitational potential energy is due to the position above the Earth. So the potential energy of 3 is the highest. 2 and 4 are equal. It doesn't matter which way they're moving. The potential energy is just due to the position at that moment. And 1 is the lowest. So we'd say 3 is greater than 2, which equals 4, which is greater than 1. The zero of potential energy. Amber and Carlos use coordinate systems with different origins to determine the potential energy of a rock. No matter where the rock is, Amber's value of potential will be equal to Carlos's value plus 9.8 joules. Alright, so Amber's origin is on the ground, whereas Carlos decided to make his origin be where the rock is at the current moment. Why is it Amber's is always 9.8 higher? Because it's a 1 kilogram rock raised 1 meter. So MGH would be 1 times 9.8 times 1. That's why she's got a potential energy that's 9.8 joules more than Carlos. Because for him, the rock is at a height of 0, the way he's defined the system. If the rock moves, both will calculate exactly the same value for the change in potential. So even though they start with different values, their change in the value will be the same. In problems, only the change in potential has physical significance, not the value of potential in itself. So in our physics problems that we do as physicists, really the change in potential energy is what is significant, not just the brute value of potential. Okay. Energy bar charts. A ball is tossed up into the air. The simple bar chart below shows how the sum of kinetic plus gravitational potential remains constant as the pebble rises and then falls. So here at the beginning, that's when the ball is at its fastest, like when it first gets thrown or kicked or whatever. Potential energy bar chart is at this total energy constant line right here, whatever that total energy constant line is. Potential is nothing because it's at the origin of position, which means its position, its height is 0. Here in the middle, you have somewhere in here the kinetic energy is decreasing because the ball is going slower. Potential energy is increasing because the ball is going higher, and at some point they will equal each other. Then at the very top, no kinetic energy because the ball is still for a moment. All the kinetic has become potential. Potential is at its peak, so the potential is at that total energy constant line right there. Then it comes back down, same thing but in reverse, and so here the the potential energy is decreasing because it's getting lower, but the kinetic energy is increasing because it's speeding up. And they hit a moment where they're equal. And then when the ball gets back down to the origin of height, that's when it's at its fastest. And so the kinetic energy is at its peak, and the potential energy is now back down to 0. All right, 10.2, dropping a watermelon. That sounds fun and delicious. 5-kilogram watermelon is dropped from a 3rd-story balcony, 11 meters above the street. Unfortunately, the water department forgot to replace the cover on a manhole, and the watermelon falls into a 3-meter deep hole. How fast is the watermelon going when it hits bottom? Okay, so we can do this with an energy transfer kind of a problem. We could also do dynamics and kinematics, where we do this, the whole thing where we do the force and get the acceleration and then do kinematics. We could do that, but this is actually probably easier here. So a 5-kilogram watermelon is dropped. Okay, so at the beginning, all the energy is potential. If it's just let go, then at the moment it's let go, it has no kinetic energy because it's not moving for that split-second moment, so it's all potential. So we're going to say Ui plus Ki equals Uf plus Kf. So potential energy is mgh. So the mass, so this is mgh plus 1/2 mvi squared equals mghf plus 1/2 mvf squared. Alright, so this is going to be 5 times 9.8 times, and now how high is it? You could do this different ways. You could make the origin be the ground, and then it ends up at -3 as it falls. Or you could just let the origin be down here at 0, and then instead of this being 11, this would be at 14. So you could define your system either way. So I think to me it makes more sense to I'm gonna make my origin down here where it finally hits at the bottom of the manhole. So that means that my initial height, instead of being 11, is going to be 14. And the initial kinetic energy is 0, as we've said. Now at the very bottom here, at my origin, when it gets to the bottom of the manhole, that's what I've made 0, so its potential energy is going to be 0. And its kinetic energy is going to be 1/2 m. Well, let me put m in there. 1/2 times 5 times Vf squared. And that's what I'm looking for. I'm looking for Vf. So, if we do the arithmetic, notice that the 5's could cancel out. Do that arithmetic, and we should get, here's the energy bar chart that they kind of do. They did it with the last thing being -3, which is totally fine. So if they do it that way, the bar chart would look like this. It would be 0 kinetic at the beginning, some potential. Then at the end, the kinetic energy is actually above what the potential energy was. But the potential energy is now negative because you have a negative position, so it accounts for it. So either way you go, it's going to be fine. Alright, we do the arithmetic, and we should get the square root. Vf is the square root of what all that stuff, so it should be plus or minus 17 meters per second. And I think we'd want to say negative 15 meters per second, 17 meters per second. Because it's going down, the velocity is negative. Alright, gravitational potential energy continued. The figure shows a particle of mass m moving at an angle while acted on by gravity. The work done by gravity is, okay, gravity doesn't move it, doesn't act on it according to that entire delta R vector. Gravity is only affecting the vertical change, the vertical component of delta R. So that's why it can say that this just goes back to the last chapter. The work done by gravity is the gravity force vector times the delta R, or dot the delta R vector. All right, another way to get that is just to break the delta R down into its vertical and horizontal components, and you would only multiply the gravity by the vertical component. So you could use, you have to know some angles in here to be able to get that. That's just trig. Because the force of gravity has no x component, the work depends only on the vertical displacement delta y. Consequently, the change in gravitational potential energy depends only on an object's vertical displacement, not its horizontal displacement. All right, quick check 10.2. Starting from rest, a marble first rolls down a steeper hill, then down a less steep hill of the same height. For which is it going faster at the bottom? Ooh, this is a good question. All right, the work done by gravity. In which of these cases does gravity do more work? Okay. The question is, how much vertical change in position do you have with both of these things? They have a different horizontal change in position, but they have the exact same vertical change in position. The vertical change in position is equal for both of these, and that's the only thing that matters as far as the work done by gravity is concerned. So the work done by gravity on both of these marbles is going to be the same, which means the kinetic energy is going to be the same at the bottom, or you could think of it this way. The change in potential energy, which is only associated with the height, the change in height, is going to be the same for both. Therefore, they're going to go the same speed at the bottom. Okay. The figure shows an object sliding down a curved frictionless surface. The change in gravitational potential energy of the object plus Earth system depends only on delta y, the distance the object descends, not on the shape of the curve. So we could say, all right, one child slides down this slide, another child slides down this slide, another child slides down this slide, another child slides down this slide. Which child's going fastest at the bottom? They're all going the same speed at the bottom. One child slides down this slide. As long as it started at the same height and ended at the same height, that child is also going the same speed at the bottom. All right, now this is assuming, no friction, so friction may come into play here if there is friction. But assuming frictionlessness, if that's a word, then what I just said would be true. Okay. The normal force is always perpendicular to the box's instantaneous displacement. And so the normal force in this case, because it's always perpendicular to the movement, it's doing no work. Quick check 10.3. A small child slides down the 4 frictionless slides, A through D. Rank in order from largest to smallest her speeds at the bottom. I just gave that away earlier, didn't I? But it should be D. Right, quick check 10.3. The speed of a sled. Christine runs forward with her sled at 2 meters per second. She then hops onto the sled at the top of a 5 meter high, very slippery slope, so frictionlessness then. What is her speed at the bottom? Well, we can say this. We can say Ki plus Ui equals Kf plus Uf. You might end up liking doing this kind of stuff. I'm kind of liking it. So what is her initial kinetic energy? It's 1/2. We don't know her mass, do we? So let's just leave it as a variable. I bet it's going to cancel out. Times m times 2 squared What's her initial potential energy? It's mgh. It's m times 9.8 times h, which we're going to say is 5. If we put our origin at the bottom of the hill, then at the top of the hill, her vertical position would be 5. That's going to equal her kinetic energy at the bottom of the hill, which is 1/2 m Vf squared. Vf is what we're looking for, plus the final potential energy, which is, if she's at the bottom now, we've defined that to be a vertical height of 0, which means her potential energy would be 0. And notice now, if we ignore that now, every one of these terms has an m in it, so the mass cancels, so her mass doesn't matter. It don't matter if this was a little bitty girl doing it, or if it was a big old bear doing it. It wouldn't matter. The potential, the final speed at the bottom was going to be the same regardless. So if we do that little arithmetic there to solve for Vf, notice this is the bar chart that represents the math we just did. Initial potential plus initial kinetic. Initial kinetic plus initial potential equals final kinetic plus final potential. Now, it doesn't matter which order you go in. I just needed to say that because that's what order they put it in. And they should get 10 as the answer there, 10 meters per second. All right, we will stop right there for this video and maybe we'll make a part 2.